Foreign ships unloading materials at any harbor in the United States must have their cargo cleared through customs. U.S. customs officials use many different techniques to determine the composition of substances. One of the most widely used is a technique called gas chromatography. Samples of the substance are taken to the lab where they are analyzed. Chromatographic separations are based on the differential distribution of the components of a sample between two phases. One of these phases is held stationary, while the second mobile phase carries the components of the mixture through the stationary phase. Many chromatographic techniques using different combinations of phases have been developed. For instance, there is liquid-solid chromatography, liquid-liquid chromatography, gas-solid chromatography, ion exchange chromatography, and gas-liquid chromatography. Of all these chromatographic methods, the simple instrumentation and the fact that the size of the sample can be very small have caused gas-liquid chromatography to be one of the most widely used methods for separating mixtures of volatile compounds. When the sample removed from the ocean freighter arrives at the lab, it is prepared for analysis and then injected into a gas chromatograph, where it is immediately vaporized. The gaseous mixture is moved along the column by a carrier gas and separated into its components. Each component is detected as it leaves the column and its presence noted on a recorder. The extent of the separation of the components of this sample depends on several factors. The properties of the components of the mixture play an important role in the separation process. In gas chromatography, as in fractional distillation, the greater the difference in boiling points of the components, the easier their separation is to achieve. For many stationary phases, the separation is based entirely on the differences in boiling points of the components. The chromatographic column acts as a fractional distillation column with a very large number of theoretical plates. Components with boiling point differences of only a few tenths of a degree are easily separated. In addition, in gas chromatography, as in all other kinds of chromatography, differences in the solubility of the components of the mixture in the stationary phase enhance the ability to achieve a separation of the mixture. There are many different materials that can be used for the stationary phase. The choice depends on the mixture to be separated. Nonpolar phases, such as squalene, separate primarily on the basis of the differences in the boiling points of the components of the mixture. A mixture of hydrocarbons can be easily separated on a squalene column. Polar phases, such as carbowax, tend to separate on the basis of the different polarities of the components of the mixture, as well as on the boiling point differences. A mixture of compounds with similar boiling points but differing polarities can be separated on a carbowax column. So that a large surface area of the stationary phase can be exposed to the vaporized molecules of the mixture, the liquid stationary phase is thinly coated on small inert solid particles called the support. The solid particles are commonly glass or diatomaceous earth. The length chosen for the chromatographic column is dependent on the difficulty of separating the components. Columns may be as short as 10 centimeters or as long as several meters. The diameter of the column is usually chosen after a consideration of the amount of sample to be separated. Large diameters are used for large samples. Diameters ranging from a few tenths of a millimeter to several millimeters are common.
Animating the separation processes that occur because of differences in adsorption may aid in understanding how the separation of the mixture occurs within the column. If we assume these large beige circles represent the stationary phase packed into the column, it can be seen that there is still a lot of space through which the vapor can move. When the vaporized mixture, represented here as red and blue dots, enters the column, some of the molecules are adsorbed into the stationary phase, while others are carried along through the column. The ratio of the amount of time components spend in the vapor, compared to the time they spend dissolved in the stationary phase, depends on the relative solubility of the components in the stationary phase. However, As the remaining vapor is swept along through the column, it will also dissolve in the liquid phase and will temporarily establish an equilibrium between the liquid and vapor phases at this point in the column until the vapor molecules are again moved further down the column. In this animated sequence, the blue molecules that are strongly adsorbed by the stationary phase spend much more time in the stationary phase than in the vapor phase, and thus move slowly through the column. The red molecules, which are only weakly adsorbed by the stationary phase, spend more time in the vapor phase and are moved more quickly through the column. However, some of this vapor still also does dissolve to some extent down the column. Each component establishes its own equilibrium between the vapor phase and the stationary phase continuously through the column. Because a component can only move when it is in the vapor phase, the more the equilibrium favors the vapor phase, the faster the component will move through the column. Because of this, slight differences in the equilibrium of the components result in separations. Even though there are many kinds of gas chromatography instruments, there are several basic features common to all of them. The main part of the gas chromatograph is connected to the carrier gas supply. The valves required to maintain a constant flow of carrier gas through the column are located on the tank of the gas supply and on the instrument. On the main instrument, there is a port through which the sample is injected. Behind this port is a small heated chamber in which the sample is vaporized before it flows through the column. This column is contained in a separately heated oven. At the end of the column, there is a detector which is connected to a recorder. One of the most common kinds of detectors is a thermal conductivity cell that senses variations in the thermal conductivity of the passing gases. The carrier gas flows across one wire in the thermal conductivity cell. On the other side of the cell, the carrier gas plus the separated components of the sample pass across a second wire. The cell senses the difference in the conductivity of the two wires. A permanent record of the detector response is obtained on chart paper that moves at a calibrated speed under a pen on the recorder. The initial step in preparing to chromatograph a sample is to select a column and place it in the oven. The carrier gas flow speed is then adjusted. A bubbler, consisting of a calibrated tube containing a soap solution, allows one to determine the flow rate of the gas through the column. Once this has been set, it should never be changed while a sample is on the column. There are 3 sets of temperature controls on the chromatograph. One set for regulating the temperature of the vaporizing chamber, one set for regulating the temperature of the column, and one set for adjusting the temperature of the detector. Since it is necessary for the sample to enter the column all at one time as vapor, the temperature of the vaporizing chamber behind the injection port is set well above the boiling point of the highest boiling component of the mixture. Within the column, where it is necessary for the components to equilibrate between the liquid and vapor phases, the temperature is set lower than the temperature of the injection port. Chromatographs with thermal conductivity detectors have a third temperature control that regulates the temperature of a resistance wire in the detector. The temperature of this detector is normally set according to the manufacturer's or instructor's directions. It is usually a function of the instrument rather than the sample. Before turning on the filament current in the detector, make sure that the carrier gas is flowing through the instrument. Otherwise, the filament current may burn out the wire. The attenuator knob on the recorder regulates the ratio of the pen response to the detected signal. To ensure a quantitative analysis of the sample, the knob must be set before the sample is injected. An increase in the attenuator setting results in a decrease in the pen response. Doubling the attenuator setting will halve the pen response. Obtaining the right attenuator setting for a specific sample is often a result of trial and error. If there is no prior information on the appropriate setting, a low setting should be used so that all components of the mixture will be detected. The baseline is set on the recorder using the pen adjustment knobs. The baseline should be set slightly above the edge of the paper in order to accommodate any drift while the chromatogram is being recorded. If accurate peak heights are to be measured from the chromatogram, the baseline must not be readjusted when a peak on the chromatogram is being recorded. At this point, all the controls on the instrument are set and the sample can be separated on the chromatograph. To conserve paper, the chart paper drive is turned on just before or as a sample is injected. To inject a sample, it is first drawn into a microliter syringe. The volume of sample used depends on the column length and diameter. For many purposes, 1 microliter of sample is sufficient. Holding the needle tightly to prevent it from bending, it is pushed through the rubber septum of the injector port as far as possible to get the sample into the vaporization chamber. The plunger is depressed rapidly and smoothly. Always hold your thumb or palm on the plunger so that the pressure of the vaporized mixture does not eject the plunger. As the needle is withdrawn from the septum, the position of the pen on the chart paper at the time of the injection is marked. The syringe is then rinsed several times with clean solvent. The sheath is placed over the needle, and the syringe returned to its storage container. Only after the sample has come completely off the column should another sample be injected, if necessary. When satisfactory chromatograms of the samples have been obtained, the chart paper drive is turned off. The retention times of each of the components can be measured and compared with the retention times of pure samples of the components. Since the chart paper is moving at a fixed speed, the retention time, or time required for a component to come through the column, is proportional to the distance between the point marked on the paper at the time of the sample injection and the maximum of the peak for the component. Because the pen response is proportional to the detected signal, the area of the peak due to the component is an indication of the amount of the sample present in the mixture. For precise quantitative work, the response factor for each of the components must be determined. This is simply done by determining the relative peak areas on the chromatogram for equimolar amounts of the individual components. Because many organic compounds have similar thermal conductivities, this correction factor is often negligible. However, for sample mixtures with components which have different kinds of elements, and thus different thermal conductivities, ignoring the correction can lead to errors of up to 20% in the calculation of the percentage composition of a mixture. Finally, when all the chromatograms have been obtained, the gas chromatograph can be turned off. The procedure to do this is almost the reverse of the startup procedure. First, the filament current of the detector is turned off. The attenuator knob is zeroed, and the temperature controls of the oven and vaporizing chamber are turned off. However, because the time required for the detector and injection port to reach an equilibrium is long, these controls are not turned off until all work is completed for the day. If possible, the oven is open to allow the column to cool more rapidly. Before the carrier gas flow is turned off, the instrument should be allowed to cool down. After the system is cooled, check that the filament current of the detector has been turned off. Then the main valve on the gas cylinder is closed. And finally, the pressure regulator valve is turned off. The column can be removed from the oven and stored.
Since gas chromatography is a simple and fast method of determination, it continues to be used in a variety of locations. Air quality and the composition of pollutants plague major metropolitan areas. For example, in Los Angeles, the South Coast Air Quality Management District monitors total hydrocarbons, ozone levels, carbon monoxide levels, and other compounds found in the air on a 24-hour basis. At the main air quality office, there are 10 gas chromatographs, and throughout the city there are 32 monitoring stations, all of which report their findings to the main station. By the use of gas chromatography, the Air Quality Management District can identify the sources of pollution and report on the quality of air the people of a city breathe.
This is the Air Quality Management District. At the present time on Wednesday, August 5th, air quality is unhelpful for everyone with a stage 1 ozone episode in effect.